Welcome back to our course on mastering numerical method for partial differential equations with MATLAB. In our previous lecture, we explored solving a single partial differential equation with given initial and boundary conditions using PDE-PE solver. This session provided a comprehensive understanding of PDE and demonstrated the practical application of the PDE-PE solver in handling such equations. Today, we will build upon that foundation using the PDE-PE solver and following a similar approach. We will delve into the solving systems of partial differential equations. This lecture aims to enhance your proficiency in working with the more complex system, broadening your capability to tackle various challenges in numerical methods for partial differential equations. So let's delve into the lecture. This is the lecture on solving multiple partial differential equations with MATLAB Solver PDE-PE. The approach for the system of partial differential equations or multiple partial differential equations will remain same as we do in the previous lecture for single partial differential equation, and all the steps will be same, and those functions in the same way we are doing in this for the system of partial differential equations. Okay, so there is a little difference for the syntax which you need to note down, and this will help you to understand a complete process how you can implement PDE-PE solver for multiple system of equations, whether these are 2 equations, 3 equations or 4 equations in the system of partial differential equations. Just follow the step, and I hope this will help you. PDE-PE in MATLAB is used to solve the systems of parabolic and elliptic partial differential equation. In PDE-PE in MATLAB is used to solve system of partial differential system of parabolic, and PDE-PE in MATLAB is used to solve systems of parabolic and elliptic partial differential equations in one spatial variable x and time t. Here are the some steps: general form of PDEs, then step to solve the partial differential equations using PDE-PE solver. Then we put here the example solving a system of PDE. Okay, here we are choosing example for 2 partial differential equations with their initial and boundary conditions. Later on, we can easily extend for multiple equations more than 2. So here we have the general form of partial differential equation, or the for the system of partial differential equations, and you can see here Ci. So here you can see we have this equation. A system of PDEs should be written as Ci x t u del u upon del x del ui upon del t is equal to x raised to power minus m del upon del x raised to power m fi x t u del u upon del x plus si x t u del u del x, where Ci, fi and Si, these are the coefficient and I is the index of the system of equations. So these are the steps which we need to apply for the to solve the system of equations, and these steps are the same as for the one partial differential equation. So first we need to define the partial differential equation function. Then second level we need to define the initial conditions. Then after we need to define the function for boundary conditions, and at fourth level we will call the partial differential equation PDE-PE solver. Okay, and after that we need to apply here this equation, and we are given here the system of partial differential equations. Okay, 2 equations are there. So I is equal to 1 2. This will define the system, and what we do, we will have to create PDE-x1 PDE, which will define the partial differential equations, and PDE-x1 IC. This will define the initial conditions, and PDE-x1 BC will define the boundary conditions. So what we do, we will compare for I is equal to 1. So when we have the value of I is equal to 1, and we need to compare with the first equation, and we can see that after comparing the value of C1 is equal to 1, and the value of F1 will be equal to del U1 upon del x, and that of value of s1 will be equal to u2. S1 is equal to u2. When we have I is equal to and compare this equation with the second equation, okay, so the value of c2 here will be equal to 1 and that of f2 will be equal to del u2 upon del x, and the value of s2 will be equal to minus u1. Okay, so these values are required to write the first function for partial differential equations. Okay, so now this is the function which is required to store the values PDE x1 PDE. So these are the input argument x tu dx, and these are the output coefficients and argument here CFS. So the value of C1 is equal to 1 and C2 is also we have is 1. So this is C1, this is C2. So both the values will be stored in C. Then we have this is the value of F1 and this is the value of F2. F1 and F2 both are stored here. One is used for the index for the first differential equation, and this is for the second partial differential equation du dx1 du dx2. Okay, and this is the value of s1, this is the value of s2. So both the values are stored here for s. So these functions will always remain same. Just in the same way you can extend by using this semicolon for more system of equations, but here we have the example for two system of equations. Okay, now then after we need to write the initial condition function. Okay, so here you can easily observe that u0 is used for the initial condition and PDEx1 IC initial condition, but here we have two system of equations and both have different initial condition. So this is the initial condition for the first equation and this is the initial condition for the second condition. Okay, and both will be stored here for u2. Okay, so u0 it will be equal to either this one or this one according to the system of equations, and we need to save this function in MATLAB with this name. Okay, so now come to for boundary conditions, and here you can observe that the signature is same which we do in the one partial differential equation, and same index we are using here, but the how we can use PL, QL, PR, QR, see very carefully. So here these are the left boundaries for both the equations. UL1 for first equation, UL2 for the second equation, and QL is equal to 0 here, and PR is equal to UR1, UR2. These are the right boundary values and functions, and QR both are 0 in this equation. Okay, so these are the boundary conditions, and we need to save this function in the MATLAB with this name. We need to set the initial values and call the PDEPE solver. So here the value of m is 0 due to symmetry parameter as we do in the same example. So there is no big difference. Here x we have is 0 to 1, 20, which is the special mesh, and 0 to 2, 20 time mesh, and here we will call the function PDEPE, and these are the corresponding argument same we are using here. So this will handle the partial differential equation, this will solve the corresponding initial conditions, this will handle the boundary conditions. Okay, so when we will apply this code, this will solve the system of equations, and there will be two solutions, both will be stored in solution. Okay, but we need to extract the value for u1 as well as for u2. So u1 will be equal to see this syntax colon colon and 1. So this will store the solution of first partial differential equation, and u2 is equal to solution colon colon u2. This will store the value of or the solution of u2. Okay, so these are the required solutions. Now we need to visualize these solutions, and for that we have to set the value. And here you can see these statements are used for solution of first partial differential equation. And see the syntax. Surf function, which is inbuilt function in the MATLAB, we are using here. X, T, these are the input argument, and U1 is the first solution. Then you can put the title, X label, Y label, Z label. We have solution 1, and these are the sequence of statement which is used to visualize the result of a second partial differential equation. In the very first we have this is the surface for second solution, then title, X label, Y label, Z label for second solution. Okay, so when you will execute these sequence of statement in MATLAB, you will have the graph of two solutions, one for U1 and the second will be for U2. So let's observe in MATLAB. You can see this is my MATLAB window, and the very first we have is partial differential equation function. Okay, you can see this is the partial differential equation function. Okay, PDEx PDE, and here you can see the function name PDEx1 PDE. These are the input argument, and C is equal to 1 1, F is equal to du dx1, du dx2, and S is equal to u2 and minus u1. So these are the same as we discuss in the presentation. After that we need to apply the initial condition, and you can see the same statement is here, function which we discussed for the initial conditions, and we need to save with the same name, and all the files which we are presenting here and which we have discussed must be in the same directory. Only then these will help you. Okay, and here we can see the boundary conditions for all the two system of equations. Okay, the function which we discuss are the same is we save the file in MATLAB, and here are this is the script file at which you can see the sequence of statement to visualize our results. Okay, so m equal to 0, x equal to we have 0 to 120, and t is we have time mesh. All these sequence of statement are same as we discussed in the presentation. This will plot the first graph, and this will plot the second graph. No change, everything we have discussed, just we need to visualize the result when you will run this file. Okay, press here and you can see that we have two different graphs. So the first we have is the solution of first partial differential equation according to the given initial and boundary conditions, and the second we have is this. The second is the solution of a second partial differential equation. So in this way you can easily write the code and you can plot a system of equation. Following the same, you can extend for 3 equations, 4 equations, 5 equations, whatever you have the problem, but you need to practice on it. And along with I will add some more examples for you in the lecture, and 2 examples are there. You will write the code and try yourself. Okay, so this code will be provided in the Power presentation. So both the examples for your assignment. As we conclude this lecture, we have successfully extended our understanding from solving single partial differential equation to tackling system of partial differential equations using PDEPE solver. This progression underscores the versatility and power of MATLAB in addressing complex numerical problems. By mastering these techniques, you are now better equipped to handle a wide range of real-world applications involving system of partial differential equations. Remember, the skills you have developed here are fundamental tools that can be applied across various fields of science and engineering. Thank you for your attention and engagement. In our next lecture, we will continue to explore advanced numerical method, further enriching our toolkit for solving partial differential equations. Until then, keep practicing and experimenting with these concepts to solidify your understanding. Until then, keep practicing and experimenting these. Until then, keep practicing and experimenting with these concepts to solidify your understanding.